and in today's video, we are going to go over plate tectonics and the dynamics of the Earth's lithosphere and mantle. Wow, I haven't went over this since my Earth science days. Okay, okay, so we're gonna learn about the Earth's composition and the layers it has. Oh, continental drift. Oh wait, there was a song. Alfred Winnegar? Yo, I forgot. There was this really good song though. Oh wait, no, I'll find it. I'll find it. Oh shoot, don't listen to that. Uh, uh, this is song. Hold on, I'll find it. I'll find it. I'll find it. Oh, Alfred, yeah. Wait, is this copyrighted? Uh, oh god damn it, it's copyrighted. Are we dead ass? The Switch of Continental Drift by Alfred Weg and it's looking good. But okay, so we're gonna also understand how does the internal heat of the Earth drive the physical reconfiguration of continents and oceans over geological time. Okay, so first we're gonna understand the structure of the Earth. So the Earth is stratified into different chemical layers based on density, the planetary differentiation. And first we have the crust, which is the thinnest skillet, which is almost like the skin, and it composes the continents and the ocean. And then we have the mantle, right here, the crust, mantle, which is the semi-solid pyroidite, which is 84% of the Earth's volume. And then we have the outer core, which is made out of liquid iron and nickel. And this is where the magnetic field source comes from. And then we finally have the inner core, which is a solid iron slash nickel due to extreme pressure. So looking at the mechanical layers, we're gonna first look at the plates with the lithosphere, which is the rigid outer shell, including the crust and the very top of the mantle. And this layer is broken into tectonic plates that moves as discrete units. And then we have the asthenosphere, which is the plastic deductible layer of the mantle, and it's directly beneath the lithosphere, and it is capable of slow flow, allowing the plates above it to slide. Next, we're going to talk about continental drift. So, before the continents, we had the 7 continents. Alfred Wegener proposed that the continents were once joined into a supercontinent right here called Pangea. And that's because he looked at the coast and saw that it fits like a jigsaw. And then also he saw fossil evidence like identical land-based fossils on separate continents, like this lizard or this fossil remain of a reptile here and here. And if it was like separated by a big ocean, there would be no way. But if it was connected, then it would be able to have the fossils in both places. And also rock formations with matching mountain belts like the Appalachians and the Caledonians. Okay, so the driving force is mantle convection. As you can see, goes up, goes right, back down, and goes straight back up. And the plates do not move on their own, but they're actually part of the massive heat transfer system. Oh, I remember this in Earth Science. We had a really, I'm gonna just say Mr. Craig. We made him play Monkey Mart during class because we were such a good class, you know. But hot, less dense mantle material rises as the ridges cool and sinks back down at subduction zones, and then this creates a circular convection cell. And then the secondary force is a slab pole, which gravity pulls it by sinking plates, and a ridge pole. As you can see here, the slab pole pulls it that way. There's a trench, so it goes down. The lithosphere is that. So, and now we're gonna talk about the free plate boundaries. We have divergent, which is moving apart, and that creates constructive new crust. And an example is the mid-Atlantic ridge. And convergent means they're moving together, which is destructive subduction, and that's like the Himalayas and Andes Mountain. And a transform is like when they slide past each other, which is conservative, which is no change, and that's like the San Andreas fault. That's how earthquakes happen too. Okay, so we have divergent, which is sea floor spreading right here, as you can see. At mid-ocean ridges, magma rises from the mantle to fill the gaps created as plates separate, and this creates volcanoes. And evidence for it is like the paleomagnetism, which is strips of normal or reserve polarity, and this is new oceanic lithosphere is born here, and that's how that's created. And then when we talk about convergent right here, as you can see here, convergent subduction is when the dense ocean crust meets the less dense continental crust, and the deep ocean trench where the plates meet bends down, and then the volcanic arc friction and water causes melting, which fuels the volcanoes on the land, as you can see here. And then this also causes earthquakes and shallow to deep focal points. And then we can move on to the third and last one, which is convergent. This is, oh wait, no, there's one more below this, but this is when two continental plates collide, and neither is dense enough to subduct, so instead they buckle and fold, and this creates massive, massive folded mountain ranges, high systemic activity but minimal volcanism. And the example is the Indo-Australian plate hitting the Eurasian plate, the Himalayas. And then finally we have transform, where they slide into each other, but no, against each other, and the plates slide horizontally past one another, and the jagged edges lock together until pressure overcomes friction, and no crust is formed or destroyed, and this results in frequent shallow earthquakes in linear valleys and offset stream beds. Next, we can talk about the intraplate volcanism, which are hot spots like here. And this is when some volcanoes occur far from the plate boundaries, and these are caused by stationary mantle plumes. And as the tectonic plates move over the plume, it leaves a trail of extinct volcanoes, which only the youngest become active. An example of this is like the Hawaiian island chain, where Kauai is old, eroded, and Hawaii, the big island, is currently active, as you can see here. You can take a picture, you can pause the video and take a look at these figures. These are pretty nice figures, I'm not gonna lie. Okay, so we can talk about the rock cycle with melting, which is subduction, where old sedimentary and metamorphic rocks are pushed into the mantle, meeting into magma, and that's what igneous precursor is. And then we have uplift, which is collision, where pressure and heat transforms rock into metamorphic layers, then uplift them to be weathered into sediments. This is the Earth's massive recycling engine of the rock cycle. Next, we can move on to a practice problem. Okay, so a researcher finds a chain of volcanic islands in the middle of an oceanic plate. The islands get progressively older the further west you go. What's the most likely cause? I'll give you a minute to solve this. Uh, hmm. Hmm. Yo. Okay, so the answer is C. The ocean plate is moving westward over a stationary mantle hotspot. Okay, so we're just gonna go over a basic summary which is what you need to remember about convection, which is which drives the plate movements. The lithosphere moves on the deductible, the asthenosphere. Divergent boundaries create new seafloor, convergent boundaries build mountains, and transform boundaries are conservative zones. And just remember, Earth is a living and moving puzzle powered by heat. And here's some of just like the image sources where I got my sources from. I hope you enjoyed this video, maybe learned something or two, and I'll see you in another video. Bye.